So now next, let's derive the, well, derive, as I said, is not the right word. Fundamental laws of physics cannot be derived. They can only be guessed. Okay? Because we don't know why nature chose this equation rather than that equation. We just don't know. It's there are even like schools in theology which say that all that the Creator knows are the general laws of the universe. That the Creator is not interested in the fates of us individuals. So, yeah, it's like the blind watchmaker or something like this. Okay, so right. Anyway, so if particles are determined, if the particle behavior, if the of matter particles we are not dealing with light here, and I'll let you know, I'll tell you why, are determined, or you should, I don't know what should I say, are described, yes, by a wave, then there better be an equation for that wave, right? So Schrödinger discovered such an equation for non-relativistic particles. So for non-relativistic particles, the energy should have a kinetic part, which we write as p squared by 2m, and a potential energy, right? Now, according to Einstein, and extended to matters by de Broglie, E should be given by h bar omega. So Einstein only said that E equals to h bar omega for photons, but de Broglie said, well, why not extend it also for matter particles? If they are going to have a wave associated to it, we can probably have a frequency, and therefore we can relate them to, we can associate h bar omega to those waves. And according to the de Broglie relationship between momentum and wave number, then the right-hand side, the first term should be h bar omega k squared divided by 2m plus v. So any wave equation that we derive must yield as the energy relationship, this equation. Okay, this is the constraint. This is the condition that we must satisfy. Okay? So wave equations usually have time derivatives, right? Wave equations have, we saw they have time derivatives and space derivatives, right? So let's try the wave psi. So we are trying this. This is an ansatz. That's why I put a question mark there. This guess may not be the right guess. An amplitude times sine of kx minus omega t. And what I'm assuming here is that, by linearity, once we figure it out for this pure sine wave, we can figure it out for any wave packet, okay? Because in reality, the realistic particles would be given by wave packets, not pure sine waves or cosine waves. Okay? So if I try this and then take the first time derivative, what do I get? I get minus omega a cosine of kx minus omega t. And we cannot go beyond the first time derivative because in this relationship consists of only the first order in omega. So my wave equation cannot have more than one time derivative. Okay. On the other hand, this relationship has second order in k. So if this is going to be the solution to my wave equation, then it must have second order time space derivative. But if I take second order in space, I get k minus k squared a sine of kx minus omega t. Okay? And we have a problem because in any equation which contains this term and this term, we will get k squared and omega as needed, but the sine function and the cosine function will not cancel out. And therefore, we cannot get this relationship because there will be sine and cosine, which will not cancel out. Okay? So this ansatz doesn't work. So we have similar problem if I take the ansatz where instead of a sine, I have a cosine. And this all has to do with the fact that there is a second order in k and a first order in omega. So what do you think I should do?
Sir, we try e to the power kx minus t, ওটার ডেরিভেটিভ নিলে তো মানে চেঞ্জ হচ্ছে যেমন সাইন কোসাইন হয়ে যাবে তো
So you're saying psi should be equal to a e to the power? Yeah?
e to the power kx minus omega t. Yes, sir.
So Nyan is suggesting e to the power I kx minus omega t. Let's see if this works, okay? So if I do d psi by dt for this guy, I get one factor of minus I omega coming down, but then this is the psi, right? This is the beautiful property of the exponential. If you take its derivative, you get it back. And if I take second order in psi, in the space derivative, I get two factors of ik. So I get minus k squared of psi. So now if I write down the equation I h bar d psi by dt is equal to minus h bar squared by 2m d squared psi by dx squared plus v of psi. Then using these two guys, I get here I get minus I times I is plus. So I get on the left-hand side h bar omega times psi. On the right-hand side, this minus gives me plus. So I get h squared k squared by 2m times psi plus v times psi. And of course, psi is common to all of this, and therefore we get the required relationship h bar omega is equal to h bar squared k squared by 2m plus v. Perfect. So we can now, so this is essentially the Schrodinger equation, but this is in one spatial dimension. So if I have to, what can I do to generalize it to 3 dimensions? I just replace this by the Laplacian. So in that case, we can do the same thing, but instead psi will be now a times e to the power I, the vector k dot x minus omega t. And then we are going to have the equation I h bar d psi by dt is equal to minus h squared by 2m, the Laplacian acting on psi, plus v, the potential function, which we will take it to be for now time independent. It doesn't have to be. A psi. And this is the Schrodinger equation, the Schrodinger wave equation. I should say the very famous Schrodinger wave equation. So before we go on and discuss this and take some, questions, let me give you an alternative form of this equation. And we can define H, it's a linear differential operator. It's called the Hamiltonian. And it's defined to be minus h squared by 2m, the Laplacian, plus v. And the eigenfunctions, or the eigenvalue equation, of the Hamiltonian which is h hat acting on the eigenfunction with eigenvalue e is equal to e times. So this equation is called the time-independent Schrodinger equation, okay? And so this equation also plays a very important role in quantum mechanics. It's the same equation, but this is the time-independent version of it. This is called the time-independent Schrodinger equation or Schrodinger equation. Okay, so do we have any questions or comments so far? We see that Nian's guess was right. Let me just flash both equations. Okay, can you guys hear me?
Yes.
Yes, sir.
Sir, did the
Okay, no-
time dependent?
Sorry,
Sorry.
I can't hear. I think you're too close to the microphone or something.
Sir, how did the time-independent Schrodinger equation come about?
How can it be time independent? Is that the question?
How did time-independent Schrodinger equation come about?
So we had this relationship. If we just replace the left-hand side by E, then we have essentially, if we identify that, then that's the same as this equation, right? The thing is that we use this guy as a test solution, but by linearity we know that it doesn't have to be the only solution. There can be any number of solutions which are linear combination of these guys, right?
Got it.
Okay. Any more questions or comments?
Is psi sub E different from the psi we were working with previously?
Yes, it is. They're related, but you will see in the future that psi of x and t is going to be e to the power minus I e times t by h bar times psi of e of x. And it'll be, sorry. So basically, it'll be a linear combination of all these guys, okay? In the future, so, okay. We didn't have to write, this here, the E subscript, but I just, I can just, write the left-hand side as E times psi, right? Because the left-hand side gives me h bar omega, which is equal to E, right?
Yeah.
So yeah, look at it like that. But let's go back to this guy, okay? Because when we talked about the wave equation in 1 + 1 dimension, the wave equation that we studied was this. Right? This was the wave equation we studied, right? And there, the second order in time and space was important so that it would describe a wave traveling both to the left and the right. But here we have a wave equation which is first order in time and second order in space. So you might say, does this actually, still enable us to describe particles which are traveling to the left and the right? Is it consistent with the homogeneity of space? And the answer is yes, because this thing is independent of the sign of k. And this is going to be a solution no matter what the sign of k is.